What I'd like to do is continue the discussion of calorimetry. We have a couple of problems to take a look at, and then we will get into standard heats of formation, standard enthalpies of formation. And that should pretty much wrap up chapter 5. So next week, we'll start looking at chapter 10, which is gases. So the order of this course is chapters 3, 4, 5, and then we go to 10, and then we will come back to 6 after we do 10. Okay. So let's take a look here. We were talking yesterday about this calorimetry equation. Q equals mc delta T. We also said that there was an alternate form of this equation used in your textbook, which was Sm delta T, where m is the mass of the substance that is either absorbing heat or releasing heat, transferring heat one way or the other, to or from. The C, or S, in the second equation, is the specific heat capacity, which can be defined as the amount of heat that a substance, 1 gram of a substance, will absorb such that its temperature changes by 1 degree Celsius or 1 Kelvin. Okay, that's called the specific heat capacity. We can look up specific heat capacities in general in tables online or in reference manuals. Delta T is the change in temperature of the substance. So a substance either loses or gains heat, it's absorbing or releasing energy in the form of heat, and the amount of energy that it's absorbing or releasing is equal to the mass times the specific heat capacity times the change in temperature of the substance. So we looked at a couple of problems. What we're going to look at now is what's called the molar molar heat capacity. Okay, so I'm going to flip us over to the first Alex problem. On this, okay? So we're calculating the molar heat capacity. I'll talk a little bit about what that is in a moment. A chemist carefully measures the amount of heat needed to raise the temperature of 858.0 milligrams of C4H6O2 from 20.0 degrees Celsius to 35.7 degrees Celsius. The experiment shows that 21.6 joules of heat are needed. What can the chemist report for the molar heat capacity of C4H6O2? Okay, so notice what's given here. We're given the amount of heat Q, 21.6 joules. We're given the mass of the substance, right? 858.0 milligrams. So we have the mass of the substance. We have the heat of the substance. We also have delta T, right? We have the original temperature, Ti, the initial, is 20.0 degrees Celsius. The final temperature is 35.7 degrees Celsius. So we have Q, M, and delta T. The only thing we don't have is C, right? We don't have the specific heat capacity. But be careful with this one. It gives us the formula of the substance and asks us for the molar heat capacity. So what I want to do is I want to talk a little bit about the difference between molar heat capacity and specific heat capacity. But before we do that, let's calculate the specific heat capacity just like we would have in a previous problem that we talked about yesterday. So we'll look at that first, okay? So we have that Q is equal to mc delta T. We have that the amount of heat transferred is 21.6 joules. We have that the mass of the substance is 858.0 milligrams. And then we have that the initial temperature is, sorry, let me bring this over here. The initial temperature is 20.0 degrees C. And the final temperature is 35.7 degrees C. So we can calculate delta T from that. So our first step, before we get into the idea of molar heat capacity, is let's take a look at calculating just the specific heat capacity, the specific heat for short. So using this equation, we can rearrange it to show that C, specific heat capacity, is equal to Q over M delta T. Okay, so let's do that calculation first. In this particular problem, what I'm going to do, because generally the specific heat has the units of joules per gram degrees C, I'm going to go ahead and calculate the mass in grams. So let's calculate the mass in grams to begin with. So there's different ways you can do that. 858.0 milligrams. Remember, milli is 1 times 10 to the minus 3. So we could just, define this as essentially you're translating it. 858.0 milli times 10 to the minus 3. And then that would be grams. So that would be one way to convert it. Now it's a little awkward. It's not in scientific notation. You can certainly enter that into a calculator. You can do it a different way, which is you can take your 850.0 milligrams and you say essentially 1 milligram is 1 times 10 to the minus 3 grams, right? That's a milligram. So if you multiply your 858.0 milligrams and put the grams in the numerator, you get the same answer, 858.0 times 10 to the minus 3 grams. Now, if you want to clean that up and put it into scientific notation, you just move the decimal point 2 places to the left. 2 places to the left will make the exponent more positive. Left is positive. So you have 8.580. And then you're moving it 2 places, so 10 to the minus 1 grams. Now that's a little awkward right there. Generally, what people would do is they would just move it 1 more place and just move it 1 more. And then you have 0.8580 grams. You get rid of the 10 to the minus 1 completely. So either one will work. Any of these will work for your calculator. Your calculator should have that function that it could use this one, or this one. All 3 of those will work. Okay, now that's in grams. So let's calculate C. C would be the heat, which is 21.6 joules. We're going to divide that by the mass in grams. So 0.8580 grams. I'm going to pick that last one because it's easiest for me. Let me order this a little bit better. Sorry. And then we're going to do our delta T. So our delta T is 35.7 minus 20.0, which is what, 15.7? And now we have our specific heat capacity. So we have 21.6, just estimating it, 21 over 15 is a little more than 1. We're going to divide it by 0.8, which is a little, you divide something that's a little bit less than 1, it gets a little larger. So it's going to probably be still in the ones, maybe like 1.7, 1.8, something like that. Maybe even 1.6 or 1.5. Let's see. 21.6 over 0.858 over 15.7, 1.6. So I get 1.60. And then our units are joules per gram degrees C. Okay, so that's the specific heat capacity. So again, specific heat for short. Okay, so now let's get into our molar heat capacity. So we have specific heat, and then we have molar heat capacity. It's really just an issue of units, how we quantify how much material we have. We can either do it per gram, which is specific heat, or we can do it per mole, which is molar heat capacity. There's no real shorthand name for molar heat capacity. So the symbol for this is a C. Typically, we might use C sub m here. I'm going to make that a lowercase, sorry. C sub m, okay? So that's one possibility. So now here's what we're going to do. Essentially, we know this is in joules per gram degree C. What we want this to become is joules per mole degree C. Okay, actually, let me draw that a little bit further to the right. That's all we're doing. We're just converting it from grams to moles. And we know how to do that, right? We know that we divide the mass by the molar mass to get moles. That's essentially what we do. So all we need to do then is to say the following. We have 0.858 grams. Now the formula is C4. It's given, it has to be given if we're going to do this kind of calculation. It's C4H6O2. Okay, so all I'm going to do is I'm going to convert that to moles. I'm going to convert the 0.858 mole, that's 8580, sorry. I'm going to convert that to moles by dividing by the molar mass. And then instead of dividing by the mass, as I did up here, I'm just going to divide it by moles. That's all we got to do. That's the only thing that's different. This calculation here wasn't necessary. I just wanted to show you as a review how we would get the specific heat. So what's the molar mass of C4H6O2? Well, carbon is 12.01, so that's 48.04. Hydrogen is 1.01, so that's 6.06. And then oxygen is 16.00, so that's 32. So it's 48.04 plus 6.06 plus 32, and you get 86.10. So 1 mole of this substance, C4H6O2, over 86.10 of C4H6O2. Okay, we're just dividing the mass over the molar mass. So 0.8580 divided by 86.10, and you get a pretty small number, right? Because you're taking something that's less than 1 and dividing it by something that's close to 100. So you're going to get 9.965 times 10 to the minus 3 moles. So now you have it in moles, right? Grams cancel. Okay. All right. Now we have moles. So all we got to do is, instead of dividing by the mass, I'm just going to change the equation a little bit just so you can sort of see a way to do it. Most textbooks won't give you an equation for this, but what you do is you essentially say Q is equal to NC delta T, where N is equal to the moles of the substance. We'll use that symbol when we get to gas laws, okay? And this gives us the equation for the molar heat capacity. Okay, so see, the only difference is instead of using grams, we're using moles. But the result of that is that, I'm sorry, so this is C sub M. The result of that is that this will now be in the units of joules per mole degree C. Okay, that's the difference right there. That's the molar heat capacity, C sub M, which is, you know, what I said it would be before. Okay, so now C sub M is just Q over N delta T. Okay, so second problem here, I just did essentially, again, I did the specific heat capacity over here just to remind you how to do that. Now we're going to use this formula, this equation for the molar heat capacity. So it's 21.6 joules again, over the number of moles, which was 9.960. Let me check that again. 0.858 over 86.10. Okay, so it's 9.965. Sorry, that's a 5. Doesn't look like a 5, did it? It's a 5 times 10 to the minus 3 moles. And then our delta T we said was 15.7. Okay. Alex might put the temperature difference in Kelvin. That's perfectly fine. 21.6 over 9.965 times 10 to the minus 3 divided by 15.7. And you get a very different value. So I'm going to round it to 138, but now it's joules per mole degree C. Or you may see it as 138 joules per mole Kelvin. Doesn't matter. A difference of 1 Kelvin is a difference of 1 degree C. So notice the magnitude of this number compared to this one here. See how it's roughly 100 times larger, right? If you go from 1 to 100, that's 100 times larger. The reason it's 100 times larger is that we're dividing by a much smaller number. We're dividing by the moles instead of the grams. So if you divide by a very small number, your ratio will be much larger. So be careful if you ever look up heat capacities on the internet. You have to pay. I've fallen into this trap myself. You look up a value, you need it for a problem, and then you end up with this wrong number. If you're going to get numbers that are, say, around 1 or a half, 0.5 or 2 or 3 or 4, that's typically, using the specific heat capacity. So that's usually, per gram. If you have values that are in the hundreds, that's typically per mole. So it's the molar heat capacity. But it could be even more complicated. There are other units out there. So for example, there are joules per kilogram degrees C. And so you definitely be aware of the units you're looking for or you're looking at when you look these values up online. Okay, so 2 formulas, very similar. This one's the specific heat capacity, C, and then this is the molar heat capacity, C sub M, for that one there. Okay, so there you go. So not that different, just yet, you can make mistakes on this one because you don't recognize that, oh, it's asking for the molar heat capacity. Okay. So we have one more type of problem to take a look at. So let me share this over here. Okay. And this problem is called a basic calorimetry problem. Now, this basic calorimetry problem is really a physics problem. It's really a heat transfer problem, not involving any chemical reaction here. But typically we want people to be able to do that. Okay, so here's a calorimeter. This is called a calorimeter. A calorimeter is a device we would use for measuring calorimetry, for measuring heat. So typically the way it's done is with an insulated container. So this could be as simple as a styrofoam cup. A cheap styrofoam cup would work as this because it's a very good insulator. It has air, air mixed in with the plastic. And it's very porous plastic. You could be a little bit more sophisticated and use a thermos. You could purchase a thermos, and they make these thermoses now that are really quite amazing, right? They can keep hot materials like hot coffee or something like that hot for a long time, right? So those are really good insulators. You can design insulated cups that are just amazing. But in any case, what the insulator does is it ensures that any heat transfer that occurs is very, very slow. It just slows down heat transfer. So if there's heat transfer occurring, it's only within the container. It slows it down such a degree that you make your temperature measurements. By the time you're done, essentially no heat has transferred out of the container. So that's the idea of an insulator. Okay. So there's a thermometer, and that's how we measure delta T, right? We measure an initial temperature, we measure a final temperature, and we calculate delta T. We can also measure masses of substances before we put them in, right? So if I have an object here, a sample in this case, I measure its mass, and then I can dunk it into the water. I might measure the mass of the water as well, so I know how much water there is. And then I have this insulated container here. Typically, if something is constant pressure, what you do is you allow this lid, which is keeping heat from escaping or transferring quickly, you make the lid kind of loose so that the air can keep the pressure on the inside. Air pressure will be able to move into here and keep the pressure constant. Constant volume is the case where you lock down, you screw down this lid so that air can't get in or out. And that means the pressure might change in here, right? It might change a little bit. Okay, so this has water and has a sample. So let's read the question. A 51.3 gram sample of polystyrene is put into a calorimeter that contains 300.0 grams of water. The polystyrene sample starts off at 97.1 degrees Celsius, and the temperature of the water starts off at 21.0 degrees Celsius. When the temperature of the water stops changing, it's 25.4 degrees Celsius. So you got 3 temperatures here, right? The pressure remains constant at 1 atmosphere. That's telling us it's at constant pressure, so this lid is loose. Calculate the specific heat capacity of polystyrene according to this experiment, and be sure your answer is rounded to 2 significant digits, okay? So this differs from the problems we've done thus far in that there are 2 materials. And what we're going to claim here is that one substance is going to transfer heat to another substance. So the question then is, how does that happen? We talked about it at the beginning of our discussion of heat. When something is hotter, then if one object is hotter and another object is colder, and you put them into contact, heat will transfer spontaneously from the hotter object to the cooler object, right? So for example, if I take, I guess, this mouse, and I were to somehow get this thing down, you know, put it in a freezer for a day, 0 degrees, or actually -5, -10 degrees Celsius, right, in the freezer. And then I were to put this in a warm room. So say this is at 30 degrees Celsius. If I put them into contact, that's called thermal contact, the hotter object will spontaneously transfer heat to the colder object through, again, molecular collisions. So over time, this hotter object will become cooler. The cooler object will become hotter, and eventually they will reach what's called thermal equilibrium. They will reach the same temperature. And so in this particular problem, the reason there are 3 temperatures given is that you have an initial temperature of the first object, maybe the hot object, maybe the cold object, an initial temperature of the other object, maybe the cold object, maybe the hot object. And then once they're in contact, given enough time, they will be at the same final temperature. So that same final temperature has to be given, or is generally given in these problems, okay? So let's take a look at essentially what happens here. I'm going to make the claim that when we do this kind of problem, so here's our polystyrene, and it's in water, right? So there's what's called a water bath. Whichever substance starts off hotter is going to transfer heat to the substance that's colder. So let's write down some of the numbers here. So the temperature of the polystyrene is equal to 97.1 degrees C. Probably the hotter substance, right? The temperature of the water is 21.0 degrees C. So clearly this one's hotter, right? And this one's colder. So that means that essentially what's going to happen is heat is going to transfer from the polystyrene into the water. Okay, and then the final temperature, all right, this is TF, is going to be equal, they give it as 25.4 degrees C. So this is going to be the case for both substances. And this is called thermal equilibrium. Now, again, the quality of this problem is only as good as the quality of the experiment that's performed. So if the insulator that we're using is a very poor insulator, or the quality of the thermometer we're using is very poor, then, you know, the numbers we're getting are not going to be all that great. But if we have a good insulator and we have a good thermometer, we can actually do this experiment pretty well. Okay. Now, what I'm going to claim is we're going to neglect any heat losses, right? So we're going to claim that none of the heat goes escapes or goes somewhere else, right? And again, that's probably not true. There's probably some, but again, it depends on the quality of our experiment and the quality of the substances we're using. So we're going to neglect that. So now what I'm going to say is this. The heat gained by the water plus the heat lost by the polystyrene is going to be equal to 0. That's essentially saying the same thing. We're going to neglect heat losses. What we're saying is all the heat that the polystyrene transfers goes into the water. Okay, so that means those two have to be added to 0, right? If I have $100 and I give you the $100, we haven't created or destroyed any money. I've lost 100, so minus 100 for me. You've gained 100 plus 100 for you, but the total is going to be equal to 0. And that's what this equation here is saying. Okay, now you may see this written slightly different. We might write it this way. Right? We're just changing the sign, right? Essentially what I did was I subtracted the second term from both sides. So you get Q water equals negative Q polystyrene, right? So we could write it that way as well. And sometimes it's useful to write it in that form. Okay, so we've got some temperatures here. And so now, well, let me do this. I'm going to take this, let's take this form right here. Take this form right here. And I'm going to substitute in mass of the water, MW, times specific heat of the water, CW, times delta T of the water. And that plus mass of the polystyrene times C of the polystyrene times delta T of the polystyrene, that's got to be equal to 0. So do you see what I did here? This is called a substitution, right? A substitution is when you say, hey, I've got a formula for a value, Q, and instead of writing Q, I'm going to write that formula, MC delta T. So what this is saying is, this one right here is just this formula right here, just in a different, it's just represented differently. So we're using that we're using the calorimetry formula, right? Mass of the water, specific heat of the water, change in temperature of the water. Mass of the polystyrene, specific heat of the polystyrene, change in temperature of the polystyrene is equal to 0. Okay. Now, what's useful about this is that even though they don't tell you, we know that the specific heat of water is 4.184 joules per gram degree C. That's something we can always use in our problems. We know that about water. That's a specific heat. In this particular problem, they want us to determine the specific heat of polystyrene. Now, in theory, you could look that up, but the problem is polystyrene comes in many different forms. It's a plastic. It can be made in many different ways. It can have different densities. It can have different structures even. So you really, one batch of polystyrene may have a very different specific heat than another batch. So you have to be careful. So that's why they're asking for it in this particular problem. What's the specific heat of the polystyrene? Everything else is given in this problem. So let me write down some of the numbers that are given. They're telling us in the problem that the mass of the polystyrene, let me do the mass of the water first. The mass of the water is 300 grams, and the mass of the polystyrene is equal to 51.3 grams. So we have the masses of both substances, we have the specific heat capacity of water, and we've got all the temperatures. So we can do that. So let me do the two temperature changes. Let's do the temperature change of water first. So that would be the final temperature of the water minus the initial temperature of the water, right? So what is that going to be? Well, the final temperature is right here, 25.4. Both substances have that as a final temperature. So 25.4 degrees C. Our initial temperature of the water was 21.0. Well, that's a difference of 4.4 degrees C, right? So there we go. There's our temperature change for the water. So, we have a lot of numbers here. Okay. So let me I was going to make a little table down at the bottom, but I don't have much room and I don't want to erase all this. So I'm going to write these down. Or I'm sorry, going to box these off just so that you can see it. Okay. Okay, well, let's do the temperature change of the polystyrene. Again, that's the final temperature of the polystyrene minus the initial temperature of the polystyrene, right? So that would be, it started, let's do final. It ended at 25.4, right? Remember, both the water and the polystyrene are going to come to thermal equilibrium. So they both have the same final temperature. Their initial temperatures are what are different. Now be careful with this one because this is going to give you a negative number, right? 97.1 is greater than 25.4. So 25.4 minus 97.1 is negative 71.7. That's just another way of saying it got colder, right? The water gets hotter, the polystyrene gets colder. Notice they don't change temperatures the same amount, and that's because they have different specific heat capacities and they have different masses. Those are both different. So they're not going to have the same temperature change. If they had the same specific heats and they had the same masses, then their temperature change would be equal. Okay, so now look at what we've got. I'm going to check these off. We have all 5 of these. There's only one that we don't have. And that's what the question is. The question is calculate the specific heat capacity of polystyrene. Okay, so now let's do the little algebra here. We're trying to isolate this one. Okay, so suppose I had A plus B equals 0, and I wanted to know what B was. I would just subtract A from both sides, right? B would be minus A. That's simple. So I'm going to do the same thing here. I'm trying to find this specific heat capacity as polystyrene. I've got 2 terms that are added together. So I'm going to take that first term for the water and subtract it from both sides. So I'm going to rewrite this a little bit differently. Mass polystyrene, specific heat capacity polystyrene, change in temperature polystyrene equals minus mass of the water, specific heat of the water, and change in temperature of the water. Okay, now we're getting closer. But now we've got these 2 quantities times the specific heat of polystyrene, the mass and the delta T. So what do? If it's A times B, let me come over here. A times B equals, I don't know, X. If I want to know what A is, I would just divide both sides by B, right? And that would give me A. So same thing here. We're going to divide both sides by the mass of the polystyrene and the change in temperature of the polystyrene. And that will give us the specific heat, which is what we want. Now this formula ends up looking kind of funky. We've got minus mass of the water, specific heat of the water, change in temperature of the water, divided by mass of the polystyrene times change in temperature of the polystyrene. Okay, so don't forget that negative there. In fact, I'll put a parentheses here. You don't have to, but you can put a parentheses in there, you know, just to kind of show it's the negative of this whole thing. Where did that negative come from? Because we had to subtract this one from both sides. But we also have a negative in terms of this temperature. So what's going to happen is you have 4 values that are positive, 1 that's negative, and then you have this negative in the front. So a negative times a negative is a positive. So I'm just going to go ahead and plug all these into my calculator and get a number. And so the mass of the water is 300 times the specific heat capacity water, which is 4.184, times the change in temperature, which is 4.4. Then we're going to divide that by the mass of this polystyrene, 51.3. We're going to divide it by the change in temperature, which is 71.7 negative. And then we have a negative in the formula. So what you get is 1.50. And then going through all the dimensional analysis, in terms of dimensional analysis, masses are going to have the same units. So those units will cancel. Change in temperature will have the same units on top and bottom. So those will cancel. So whatever your units are for the specific heat of water, you're going to get the same units for the specific heat of the polystyrene. And there we go. Reasonable answer. Specific heats tend to be, water's pretty high at 4. There was a problem yesterday we looked at where in the table it showed that lithium was like 5. I didn't think there was anything that high, and I still find that odd. But 1.5 seems like a reasonable answer. Okay. 2 significant digits. I'm sorry, it said to round it to 2, so that's 1.5. Okay. So practice this one. You get to go through, all of the numbers and everything. Again, the change in temperature for one of them is going to have to be negative, and the change in temperature for the other one's going to have to be positive, right? Because if something is cooling and the other one's heating, cooling is a negative temperature change and heating is a positive temperature change. And there you go. Okay. So they call that a basic calorimetry problem, and it is a basic calorimetry problem, but it does have, quite a few steps in there. So the main thing I do when I do this type of problem is I draw myself a little picture. So I'll say, hey, I'm putting this in here. Of course, they give you one, but I put this here, I put it in the water. I say, oh, which one's hotter, which one's colder? The one that's colder, the heat's going to go to it. And then you come back and you say, okay, well, we've got this equation right here. Those two have to add up to 0. And then it's just a matter of plugging in all of the numbers and solving for the one they want. Okay, so there you go. If you want to see another one, there are in YouTube, you can look at my last couple of semesters. I've done this type of problem several times, so you can look at multiple examples of this if you want to. Okay, there you go. All right, so that is it for calorimetry, and it comes toward the end of the chapter, but we shouldn't underestimate the importance of this. This is experimentally how we figure all this stuff out. So we talk about enthalpy, we talk about internal energy, we talk about heat and work. The calorimetry experiment is how we find Q. That's how we do it experimentally. And if that's how we find Q, then at constant pressure, that's how we find delta H for a chemical reaction. So delta H and Q are related to this experimental technique to figure out how things are being done. Okay. So all of this discussion is around calorimetry. Now, we have one more topic that I want to go over, which is section 5.6. And there's just a couple of different types of problems here. And this is called standard enthalpies of formation. Okay, so let me make a new slide here. So section 5.6. Standard enthalpies of formation. Sometimes referred to as standard heats of formation. Okay, and the symbol for standard heats of formation is delta, because remember, we're talking about changes. We're talking about changes in energy. H for enthalpy, F for formation, and then a degree sign for standard. So this degree sign is telling you it's standard conditions. We'll talk about that in a moment. This is what means formation, although it can be kind of confusing. Sometimes F means fusion, which is when something is freezing. There's an energy change when something freezes or melts, thaws. And so F could be used for that. So sometimes people for formation, for fusion, they'll write FUS for fusion. So let me write that down over here. So this is fusion, which is the fancy name for freezing. Okay. All right. I'll start with F, unfortunately. So let's talk a little bit about standard conditions. So we all know that substances can exist as solids. So water could be in the form of ice. But we also know that it can exist in liquid form, right? So we just refer to this as liquid water. And it can exist as a gas or a vapor. And so sometimes this is referred to as water vapor. Sometimes it's referred to as steam, depends on the condition, on the type of situation we're looking at, the context. Okay. If something is, beyond its boiling point, if water is beyond its boiling point, we typically call it steam. If it's below its boiling point, we call it water vapor. Okay. And it turns out it requires energy to undergo transition. So taking ice and converting it to water requires energy. Okay. Taking liquid water and converting it to water vapor or to steam also requires energy. And so we typically give, names to those. I'm going to call this one delta H F for fusion. And it's about 6 kilojoules per mole. So notice this is molar values. This is not per gram, but per mole. Okay. So in other words, if I have a mole of ice and I want to melt it into liquid water, it requires about 6.0 kilojoules of energy to do that. And that's an enthalpy change. There's a heat change, Q or delta H required for that. So that's the molar heat of fusion, it's called. Likewise, if I want to take that liquid water and boil it, that's vaporization. This also requires about 44 kilojoules per mole. Endothermic, right? Positive sign. So in order to go from ice to steam or ice to water vapor, it requires about 50 kilojoules of energy per mole of water. The more water you have, the more energy it's going to take. So the point of this is that the amount of energy content that a substance has depends on the state of matter it's in. In general, the more random its state, so liquid is more random than solid, the more energy it has. So liquid water has more energy than the same amount of ice. Likewise, steam has more energy than the same amount of liquid water. That's why it's per mole, so that we're saying it's the same amount of material, right? So that means the state of matter is important if we're going to come up with a table of delta H values. So these two values here, 6.0, 44, those are all dependent on the state of matter. And that is true for a chemical reaction as well. So for example, if I take, actually, let me show you a good example because I know the numbers. If I take a mole of hydrogen gas and half a mole of oxygen gas, so there's that fraction, right? I told you earlier in the course, we like fractions. And we get a balanced equation, and this is a gas. It turns out in the thermochemical equation, the amount of enthalpy change associated with that process is about 242 kilojoules per mole of water. So if you make a mole of water in the gas phase, if it's a gas, the amount of energy that's released, right? This is exothermic. Heat is released, right? Because it's negative. It's about 242 kilojoules per mole. But if I change the state of water, so I'm not changing the equation, I'm just changing the state of water. I make it a liquid. To 85.8. Okay, see how it changed? It changed because the state of water changed. Okay, it's no longer a gas, it's a liquid. Now, what's the difference? Well, if you look at it, the difference is 44. And that's right here, right? 44 kilojoules per mole going from a liquid to a gas. It requires that amount of energy. So that also tells us something about these enthalpies, which means they're additive, right? You can add these enthalpies together. A to B, B to C is the same as A to C. Okay, it's called a state function. So That's the difference between there. So now what that means then is this, if we're going to tabulate values, we have to be very careful about tabulating them in such a way that they were measured. We know how they were being measured. How did you measure this value? Did you measure it with water being a gas? Did you measure it with water being a liquid? Did you measure it with hydrogen being a liquid or a gas? A rocket that uses hydrogen and oxygen, in order to generate the most amount of energy, you have to pack as much as you can in there if you want to go up into orbit, are going to use liquid forms of hydrogen and oxygen. And those delta H's will be different because the state of matter is important. Whereas if we're going to, blow up hydrogen in a balloon, then they're going to be in the gas phase. It takes a lot of energy to get liquid hydrogen, liquid oxygen. Okay, so let's take a look at the first step in this. It's called writing standard enthalpies of formation equations. And so let me show you the first one. Write a balanced chemical equation for the standard formation of a reaction of solid potassium permanganate. Okay, so when we do these problems, what they're going to do is they're going to give you a formula. They're going to give you, they give you a formula and a name. They're going to give you a compound. So see how we have solid potassium permanganate, and they're going to give you the state of matter of that substance. All you need to do is write a chemical equation starting with the elements that make up that compound. So see how the compound has K for potassium, Mn for manganese, and oxygen, O for oxygen. You're going to write the reactants as the elements. You're going to have to figure out what state of matter they should be in, and then you're going to write the arrow to form the KMNO4. Okay, so let me show you this one. It's very simple. So they tell you want to generate KMNO4. They tell you it's a solid, so we know it's S. So here's how you go about it. You write the formula as a product in the state of matter that they tell you, and then you identify the elements. There's 3 elements. So there's K, there's Mn, and there's O. But remember, as an element, oxygen is diatomic. So don't forget that part, right? Remember the 7 diatomics? H2, N2, O2, F2, Cl2, Br2, and Di2. Right? Those are the 7 diatomics. So if you're writing the formula for a compound that has any of those elements in it, you're going to write them as diatomics. Now, the only thing left to do is to balance it and get the states of matter. So in terms of states of matter, generally metals are solids, except mercury. Mercury is a liquid. Okay, so if you ever have a metal, potassium and manganese are both metals, you're going to write them as solids. Now the nonmetals are a little tricky, right? So hydrogen is a gas. I'm just going to go over the nonmetals here. Carbon is a solid. Nitrogen is a gas. Oxygen is a gas. Fluorine is a gas. So those are all gases, starting with nitrogen. And then in the next row, for example, silicon is a solid. Silicon, the metalloids, the ones that are between metals and nonmetals, those are always solid. Okay, as far as I know, anyways. Phosphorus is a solid. Sulfur is a solid. Chlorine now, again, diatomic, this is a gas, is also a gas. And then bromine is a liquid, and iodine is a solid. Okay, everything else here is solid. Once you get down to this row, everything's a solid. Okay, only some of the elements are. You don't have to worry about the noble gases because they're not going to form compounds anyways. So the only thing left to do then, we know this is a gas, is just to balance it. There's 1 potassium, 1 manganese, there's 4 oxygen, so I'll put a 2 there. And then this is your standard enthalpy of formation equation. Okay. So what you would do then is you would look this up and in a table and use that in a different type of problem that we'll talk about later. Okay. So there you go. That's a balanced equation. It's got the states of matter and everything, and it's got, you want 1 mole on this side, so you just have to change the numbers here to balance the equation. Let me show you one more. Haha, they gave you this one. That's cool. Okay, write the balanced chemical equation for the standard formation reaction of solid, so telling you the state of matter, mercury 2 oxide. Then they give you the formula. They're very nice to give you the formula. But see how they pick mercury? That's that one metal that's a liquid. So that's the trick there. Okay. So HGO. So again, what you do is the substance that you're forming, HGO, this is always going to be balanced with this being a 1 here. Okay. That's the nature of these equations. Now, we're not going over it yet. That's the next problem, is what's delta H for this? We can look this up in a table. It's in the literature, but it's going to be tabulated in such a way as being this being a solid and this being 1 mole and everything else on the other side being the state of matter that we talked about. So what do we need? We need Hg, but again, it's the one metal that's a liquid. So we have to put that as a liquid. And then we have O2, and that has to be written as a diatomic because that's the standard condition, standard state of oxygen gas. Where did it go? Oh, there we go. Popped in there. Okay, so how do you balance this then? Be careful with these. We want this to be a 1. We don't want to change that to a 2. So that means you're going to have to make this a half, right? A half times 2 is equal to 1. And we want this to be a 1. Okay, so be careful. Don't multiply everything by 2. So there you go. So now we have a fraction. Remember what at the beginning of the course I said, hey, these problems, they make you write things as being whole numbers, and I didn't agree with that. Well, here you go. This is one of the reasons why we actually use fractions all the time. It's more typical that we're going to use a fraction for this type of problem than we would if okay, well, I made my point. Okay, let's see. Let's do one more. Okay. Write the balanced chemical equation for the standard formation. The standard is the degree sign, by the way, for the standard formation reaction of gaseous hydrogen iodide. Okay, so we're doing HI. Now, but remember, both of those are diatomics. Okay. And they said it's gaseous. Okay, just be careful. They said it's gaseous. So it's HI as a gas. And there's going to be a delta H of formation for this that we look up in a table. We haven't gotten to that yet, but we can look them up. So what do we have? We have hydrogen, but hydrogen is H2. We have iodine, that's I2. Okay, remember I went back over, I know I put it earlier, but I2 is a solid, Br2 is a liquid, Cl2 is a gas, F2 is a gas. So those are all gases. This is a gas. This is a gas. Carbon is a solid, and it's not a diatomic. S is a solid. Selenium is a solid. Tellurium is a solid. Okay. Phosphorus is a solid. Arsenic is a solid. Okay. All of these are solids. So that's not a problem. It's really, actually, now that I think about it, it's really just these ones that are gases and then H2. That one's a gas. So those are the ones that you would do as gas. Everything else, metals are all solids except for mercury. Okay. How do we balance it? We want 1 hydrogen, so put a half. We want 1 iodine, so put a half. Okay. Okay, gas. Ooh, this one right here, that's the solid. So be careful with that one. That one's the solid. There you go. Okay. And there's your balanced equation. All right, so there's a few examples of that one. Now, as I said, what we do is when we have these equations, that allows us to look up a value, and it's going to be listed under the materials. So what you'll see is there's values, for example, for CH4 as a gas, and it's going to be called delta H. I'm sorry. So this is your material. And notice the material has to have the state of matter. It has to be solid, liquid, or gas. And then you have your delta H of formation. And this will be in the units of kilojoules per mole. Okay, so this is like minus 890. I'm sorry. That's wrong. It's minus 85. Okay. You'll find, for example, there's water, which is a gas, minus 241.8. Water, which is a liquid, minus 285.8. I'm just doing these from memory. Minus 46.0. CO2, minus 393.5. Okay, so those are just a few materials. There's hundreds, thousands, tens of thousands. But the point is that these values are all measured experimentally from this equation. You know what I mean? They're coming from the balanced equation with you having 1 mole of this and everything being in the state of matter that you would expect essentially at room temperature. It's typically done for room temperature. There are tables that are done at other temperatures, but essentially it's at room temperature. Okay, and there you go. So that kind of introduces us to the last issue here. So let me show you this problem here. Which says, using the table of standard formation enthalpies that you'll find under the ALEKS data tab, calculate the reaction enthalpy for this reaction under standard conditions. So the standard conditions, that's, you know, those, that allows us to use those values that are tabulated for the equations that we were just talking about. Round your answer to the nearest kilojoule. So here's what you do for these problems. What you do is you look up the delta H of formation values in the ALEKS data table. You look them up and you tabulate them, put them right underneath the substance in the equation. And then you use this formula. Stop the share. Okay, so I'm going to show you how to do this. It's very simple. Is it 1 or 2? 2. So I'm going to look them up. And it's 227.4. And this is in kilojoules per mole. So I'm looking these values up. So I'm going to write them underneath it, 227.4. Now, H2 is 0 because if you have an element, if it's just an element under its standard condition, it's going to be 0. So this will be 0. So any problem you see where you have just elements, just call them 0. Okay. And then you look up the C2H6. And this one is minus 84.0. Okay. So now minus 86.4. So notice, I'm sorry, 84.0. Let me write that a little better. Okay. So I'm looking these up. These are in the data tab. Okay. You look them up. Now, here's what you do. You use this formula right here. Okay, so these are all what we call delta H of formation under standard condition values. it's equal to the sum of the delta H of formations of the products minus the sum of the delta H of formation of the reactants. Okay, so I'm going to do that. This is sum, which just means add. So I'm going to look, there's one product. So you do products first. So here's the product. There's only one product. So it's 1 mole, there's a 1 there, times minus 84.0. I'm not putting in the units in, I'll go back and do that. Minus the sum of the reactants. Since I'm doing the sum of more than one thing, I'm going to put brackets there. You have a 1 here and a 2 there. So 1 times 227.4 plus 2 times 0. Now, obviously, you don't have to do that 2 times 0 because you know that it's 0. So this is not an important issue, right? So, but I put it in there just so you can see, because if the second reactant is not an element, if it's a compound or an ion or something like that, then it would have a value. Okay, so then you just do your arithmetic. So this is minus 84.0, and then that would be minus 227.4. So you're going to get negative and a negative. So that's going to give you a big negative. So 84.0 negative minus 227.4, and you get minus 311.4 kilojoules per mole. Now, here's what this is cool for. What we did was we looked up these values that had been measured and tabulated, and we used them to figure out delta H for a reaction. That's what's cool about this. We now know how much energy we're going to get out of this reaction, right? It's exothermic. We now know how much energy will come out of that just by looking these values up in a table. So let's take a look at another example. Okay, same thing here. So 2NaOH solid, CaCl2 solid, CaOH2 solid, 2NaCl solid, right? So you got all these substances here, states of matter. We got to look all of those up, all 4 of them. They're all compounds. There's no elements in there, so they're going to look them all up. So you're going to take, products minus reactants. Okay, so let me write this equation. 2NaOH solid plus CaCl2 solid goes to CaOH2 solid. It's kind of a strange reaction. 2NaCl solid. Okay, I'm not sure this reaction is very easy to measure, so that if it's hard to measure it because you have all these solids, you can calculate it using these heat of formation values. So I'm going to make a little table here. So we got minus 425.8. For the CaCl2, it's minus 1228.0. For the CaOH2 solid, it's minus 985.2. And then NaCl is minus 411.2. Okay, so be careful. When you're looking these up in the data table, pay attention to the state of matter. So solid, liquid, or gas, make sure it's the same one you're looking for in the equation, okay? So now, delta H of reaction, again, it's the sum of the delta H of formations of the products minus the sum of the reactants. Very common mistake is for people to do reactants minus products. It's final minus initial. So products are final, reactants are initial. So products minus reactants, okay? So I'm gonna do the products first. So we have a 1 here. So 1 times minus 985.2 plus a 2. 2 times 411.2 minus. Now let me put this in brackets just so you can see that that first bracket is this right here. And then we're going to have the second bracket here. 2 times minus 425.8 plus 1 times minus 1228.0. Sorry, there we go. Okay, See how I have two terms here? Products, reactants. And it's important, you're gonna add all the products, you're gonna add all the reactants, and then take the difference between the two. So let me do the products first. So be careful of the negatives. 985.2 negative plus 2 times 411.2. So I get minus 162.8 minus 2 times 425.8 negative plus 1 times 1228.0 negative. And it looks like, yeah, this is gonna be a big negative number, right? This is gonna be negative 2079.6. Now keep in mind, if you're subtracting a negative number, that's like adding a positive. So you're really adding something that's a little bit negative to something that's very positive. So you're going to get an answer that's positive. So 162.8 negative plus 2079.6. And you get positive, I'll put it there, 1916.8 kilojoules per mole. These are all in kilojoules per mole. Okay. So again, this is a reaction that would be very hard to measure. I don't know how you would be able to measure delta H for this reaction because you've got a solid reacting with a solid to form a solid and a solid. This might happen in geology. So like, over millions of years, things are reacting. So if you want to know how much heat is being released or absorbed, in this case, it would be absorbed by this geological reaction that's occurring in the earth, good luck measuring it. It's too slow. And it's all solids. Measuring the temperature of a solid is not that easy, really. Liquids are much easier. So what do? You look up these values, these heats of formation in a table, which is given in your Alex tab. You plug them into this formula, and then you get that value. And then over time, you would use that as your assumption about what delta H for that reaction is. Okay, so there you go. So there's your standard heats of formation, and that wraps up chapter 5. That's section 5.6. So we've done it. So next week, I'm going to start working on gases. If you have any questions on the enthalpy stuff, you can bring that up on Tuesday when we do our lecture. At the beginning, we have time. I'm going at a pace where we have time to do that. So if you have any questions, we can do that on Tuesday. Or reach out to me if you have any questions, and good luck and have a great weekend.